Hoover High Honors Chemistry. This is Lesson 5, Discovering the Atom. So an orbital, also called a shell, is an energy level at which electrons must stay. Not necessarily stay. They can move between energy levels, but they can't move around. Other than moving from one to the other, they can't move around in between energy levels. Electrons can pass from one orbital to another, but cannot stay in between orbitals. Niels Bohr came up with the idea of circular orbitals about 100 years ago. You will learn later that the shape of the orbitals is more complex than this. Electrons in orbitals further from the nucleus have more energy. So the nucleus is trying to pull in an electron. If it were to gain more energy, it could resist the pull of the nucleus and move further away from the nucleus to a higher energy level. If it gets enough energy, it can actually break away from the atom altogether. Orbitals can be compared to steps on a ladder. You can climb up or down steps on a ladder, but you can't stand in between steps on a ladder. So yeah, that's a good analogy. If you try to step halfway between one step and the other, your foot will just fall back down to the first step, to the lower step. So think of it like steps on a ladder, those different discrete energy levels. In 1897, English physicist J.J. Thomson discovered the electron. Thomson placed a negative plate and a positive plate at opposite ends of a cathode ray tube, which caused a stream of electrons to move across the tube. By placing a magnet on the side of the tube, he caused the electrons to curve, because electrons do have a charge to them, so a magnet will cause them to move. He was able to determine the mass and charge of the electron. So over on the left, you see the negative end called the cathode, and that's like think of it like a machine gun. It's just shooting electrons across that tube. They go through a little slit over to a positive side, which is called the anode, and that's over there on the right. So as you see down on the bottom, that's an actual picture. That's it's not just an animation. And down on the bottom, you see somebody holding a magnet next to a cathode ray tube, and it causes that stream of electrons. So you're actually seeing electrons there, and you're seeing them deflect. So a negatively charged plate cathode repels electrons. A positively charged plate anode attracts the electrons, so they move from left to right. This creates a visible stream of electrons, and a magnet causes the negative electrons to change directions. And by doing this, he could calculate both the mass and the charge on the electrons. In 1904, Thomson proposed a model for the atom that included electrons. He knew that there must be positive charge to balance the negative charge of the electron. He believed that the positive charge was evenly distributed in a sphere with electrons spread around the sphere. The model has electrons, so that pink is just a generally positive sphere. He didn't know about protons, these single little particles called protons, so he just assumed it was a big positively charged sphere, and that the electrons, think of it like Jello almost, the electrons were stuck inside of it, just like raisins in Jello or chocolate chips in Jello or whatever you like to stick in Jello, bananas, whatever. The model has electrons stuck in a soft positive sphere. Now in England, this model became known as the Plum pudding model of the atom because it was a soft solid sphere with chunks of electrons. So in England they didn't have Jello, I guess back then, so they had something called pudding. It's not what we think of pudding. It's more like kind of a bready type of substance like you see there. And so that's pudding over there on the right, and if you stick little chunks of whatever, plum in it, then that's kind of what he thought this was. So this big positively charged sphere with these little negative particles called electrons put in it. Of course, we know that's not correct today, but it was just a first attempt to explain how an atom was structured. In 1911, Ernest Rutherford performed his gold foil experiment. The experiment demonstrated two things. One, the atom has a solid nucleus center, but that two, most of the atom is empty space. So rather than being this big sphere, soft sphere of positive charge, he knew that the positive charge was concentrated and it was very solid. It wasn't soft. Rutherford shot alpha particles. Now, an alpha particle is basically like the nucleus of a helium atom that we saw in earlier slides. It's 2 protons and 2 neutrons. How you create an alpha particle is not important to this discussion, but they're able to generate alpha particles, 2 protons and 2 neutrons stuck together. So Rutherford shot alpha particles, positive charge, at a thin sheet of gold foil. If Thomson had been correct, the alpha particles would have shown small deflection. They would have gone right through it. They would have just pretty much passed right through it. In fact, most showed no deflection, and some bounced back. This indicated a solid nucleus surrounded by empty space. To Rutherford, this was amazing. He said this was like shooting a bullet from a gun at some tissue paper and having it bounce back at you. He totally expected these alpha particles to pass right through the gold foil. If Thomson's model had been correct, then it had just been a soft core of positive charge. They would have done that. So here's some alpha particles represented by the red circles, and they're flying past a gold nucleus, positively charged. So the nucleus has protons and neutrons. That makes it positively charged. If the particles pass far enough away from the nucleus, they'll just go straight past. You see the straight arrows. If they come close to the nucleus but don't touch it, they'll be repelled away because the alpha particles have a positive charge. They have protons, and the nucleus has protons, so it'll kind of curve them away like you see that one doing. But if they hit the nucleus dead on, just straight on, they'll bounce back. And that's what Rutherford was seeing, that he found was amazing, that these alpha particles were just bouncing back at him or back towards him. So most of the alpha particles missed the nucleus. Some are deflected by the positive gold nucleus, and a few hit it directly and bounced back. The discovery of the proton is credited to Ernest Rutherford, who proved that the nucleus of the hydrogen atom, i.e. a proton, is present in the nuclei of all other atoms in the year 1917. So this was just a little over 100 years ago, and they're just discovering how essentially an atom is constructed. In 1932, English physicist James Chadwick discovered a particle that had the same mass as a proton but no electrical charge. This particle was called the neutron. Protons and neutrons each weigh about 1,820 times more than an electron, and we had a slightly different number before, but the number's not important. It's about that much. So if you put the nucleus of a helium atom, that's 2 protons and 2 neutrons, floating above the middle of San Diego Stadium, and the stadium were the atom, the nucleus would be 1 millimeter in diameter. So if you've seen a meter stick, and we showed it back on the measurements lesson, the millimeters, those little tiny lines that you can barely see the separation of, they're very tiny. So a nucleus would be 1 millimeter inside that entire stadium. The electrons would be in the upper level, and most of the volume of the atom is made up of empty space. Okay, so there's the nucleus. Now it's shown much bigger there than it would be. As we say, it's 1 millimeter inside that entire stadium. You wouldn't even be able to see it from the distance that you're viewing that picture from. And then the electrons would be way up in the outside in the stands, buzzing around. So that means that the vast majority of an atom, any atom, is just empty space. An isotope is an atom of the same element but with a different number of neutrons. So this is a lithium-7 atom, and it has typical lithium-7, the most common isotope, has 4 neutrons. It has 3 protons. It must have 3 protons to be lithium, and then it has 4 neutrons. So it's called lithium-7 because the 7 represents the total number of protons and neutrons added together. Now here's a lithium-6 atom. That's a less common isotope of lithium, and it has only 3 neutrons. It's still, both of them are, a term I'll introduce you to now is electrically neutral, meaning they have the same number of plus charges as minus charges, but what's different is the number of neutrons. What that means is their mass, their weight would be different. The notation for an isotope is, so for lithium-7, it would be Li with a 7 up on top, that's called the mass number, and a 3 down on the bottom, that's called the atomic number. We're going to get into those definitions here shortly. Atomic number is the number of protons. Mass number is the total number of protons and neutrons added together in a particular isotope. So these two different isotopes, one of them is called a lithium-7, the other one, the one on the right, is called a lithium-6. And the way you write the notation is with the mass number on the top and the atomic number on the bottom. So the mass number, the mass of a specific isotope on the top, and the atomic number on the bottom. An alternate notation for an isotope is what you saw before, just lithium-7 and lithium-6. Since the periodic table tells you that lithium has to have 3 protons, then you know that lithium-7 has 4 neutrons, and you know that lithium-6 has 3 neutrons. Another way an isotope can be expressed is shown here. The atomic symbol is followed by the mass number. Ions. An ion of an element is an atom that has a different number of electrons than protons. So here's a lithium atom, and it's the lithium-7, but we're not interested in the isotope anymore. So it's a normal lithium would have a mass number of 7. It's the one on the left. That's a normal lithium. So you notice that it has 3 protons and 3 electrons. So it's electrically neutral. It's balanced electrically, 3 positive, 3 negative. The lithium over on the right, though, has lost an electron. That outside electron, that valence electron, is not there. And when that valence electron goes away, the entire second orbital, you don't need to draw it because there's nothing in it. So what you have is a lithium with 3 protons and 2 electrons. So that means it has a net positive charge. It has more positive than negative by 1. So that would be a net +1 positive charge because it has 1 more positive proton than negative electron. So the lithium atom on the left has 3 protons and electrons, so the charge is balanced and the atom is electrically neutral. So electrically neutral means the charge balances. It has nothing to do with neutrons, it has to do with protons and electrons, and that there's the same number. The lithium atom on the right has 3 protons and 2 electrons and is a positively charged ion. So an ion is one that has a charge to it. A electrically neutral atom is not called an ion, only if it has a different number of protons than electrons. An anion is an atom that has more electrons than protons. So this fluorine atom, and it's fluorine because it has 9 protons. You count the number of protons, 9 protons is fluorine. Again, we'll learn how to identify that in this lesson. This fluorine atom is an example of an anion. It has 1 more electron than proton. An anion has a negative charge. So count the number of protons in the nucleus, and there's 9 protons, 9 of those plus signs. If you count the number of electrons on the outside, there's 10 electrons. So there's 1 more electron, 1 more negative charge than positive charge. So that is a type of ion called an anion. An anion is an ion with a negative charge. So the mnemonic, and a mnemonic is just a fancy name for a memory, way to remember something, that this grumpy guy is a negative ant ion. So that guy, just remember the negative ant. So negative is an anion. A cation is an atom, I should actually say an ion, that has more protons than electrons. It is an atom, but specifically it's an ion. So this lithium ion is an example of a cation. It has 3 protons and 2 electrons, which gives it a positive charge. Since it's one more positive charge, we call that a +1 charge. So this dude is a positive cation. So you see the smiling cat? He's positive. So positive is the cation. So just remember the positive smiling cat to remember that cations are positive. The atomic mass of each proton and neutron is one atomic mass unit. We talked about that earlier. An element's rounded atomic mass number tells you how many total protons and neutrons one atom of its most common isotope has. So one proton is 1 AMU, one neutron is 1 AMU. The technical definition of an AMU, atomic mass unit, is that it is equal to 1/12 the mass of a carbon-12 atom. That's the mass of a standard carbon atom with 6 protons and 6 neutrons. Now, why did they decide to define it that way? Well, because we said earlier that protons and neutrons don't have exactly the same mass. It's close enough that for our purposes we're going to say that they do. But since they don't have exactly the same mass, they take the average of the mass of a proton and a neutron, or what they do more specifically is they add the mass of 6 protons plus the mass of 6 neutrons, and then divide by 12, and they get a mass that's halfway in between a proton and a neutron. But all of those masses are so close together, the mass of a proton, the mass of a neutron, and the average mass in between them, that we just say that they're the same in this class. So you really, after learning this definition, you don't have to worry about it ever again. We're just going to say that the mass of a neutron and the mass of a proton is one atomic mass unit. An AMU gives scientists a unit of measure for mass on the atomic scale. However, it is not practical for lab calculations. We don't have a scale that'll measure 1 AMU, so what good does it do us to say that? So we're going to learn how scientists and how chemists convert AMU into something usable that we can actually measure in a laboratory. So now we're going to learn how to read the periodic table. And the typical entry on the periodic table has these 4 parts to it. So let's go through them one at a time. The top number, in most periodic tables, it's put on the top. I would say 90% of the time the atomic number is put on the top. Sometimes it's put on the bottom and the atomic mass is put on the top. So the atomic number, this is the number of protons that an element has. It is the number of protons that gives an element its identity. So if you look at a periodic table, hydrogen, the first element in the periodic table, is 1. Helium is 2. Lithium is 3. Beryllium is 4. That's how many protons they have, and that's what defines them as that particular element. So hydrogen must have 1 proton. It can have several neutrons, different numbers of neutrons, or none at all, and it can have different numbers of electrons, but it must have 1 proton, otherwise it's not hydrogen. Therefore, it's the protons and the atomic number that define the element. The atomic number is also the number of electrons that an element has in its electrically neutral state. So electrically neutral, just by definition, means the same number of protons as neutrons. So hydrogen is electrically neutral when it has its 1 proton, which it has to have to be hydrogen, and 1 electron buzzing around on the outside of it. Helium has 2 protons and 2 electrons in its electrically neutral state. Lithium has 3 protons and 3 electrons. Electrically neutral means that the number of protons and electrons are the same. An atomic number is also called a Z number. We don't use that designation a lot, but just recognize it if you see it, and you will see it sometimes. So Z number is the atomic number. The atomic symbol. This is the abbreviation for the element that is used in chemical equations. So for hydrogen, it's H. Atomic symbols are often based on Greek or Latin names, so the letters don't always seem to match the element name. For example, iron is iron, I-R-O-N. Iron is Fe, and that's ferrous, which is Greek, I believe, and it means iron. Atomic name. This is the name of the element. Atomic names can vary by language. However, the atomic symbols are universal across languages. So if we were in, say, Germany, hydrogen is called Wasserstoff. That's the name of hydrogen in German. However, they still use the atomic symbol H. So the atomic symbols, when you write a chemical formula, are universal. Any scientist who speaks any language will recognize the same chemical formula. The letters are standard, but the name can be different depending on the language. Atomic mass. This is the average of the masses of all isotopes of an element. The atomic mass is the average mass of all isotopes of an element. This accounts for the decimal number value. So here's a quick example. If 50% of an isotope, not hydrogen, but if 50% of the isotopes of an element have a mass of 3 and 50% have a mass of 4, then the atomic mass of that element would be the average of those two numbers, which would be 3.5. Look at hydrogen, it's 1.01. So let me give you an example. Let's say you had 100 hydrogen atoms, and 99 of them had exactly one proton, had an atomic mass of 1. And let's say that, so 99 out of 100 had an atomic mass of 1. And then 1 out of 100 had a neutron attached to it, a proton and a neutron. That would give it an atomic mass of 2, or a mass number of 2, I should say, a mass number of 2. So if you take 99 with a mass number of 1 and 1 with a mass number of 2 and average them, you'll end up with an average atomic mass of 1.01. So that's how hydrogen gets that decimal value. So let me take this moment to explain the difference between atomic mass and mass number. Atomic mass is what this definition says. This is the average of the masses of all the different isotopes of a particular element. The mass number is the mass of a single isotope. So if we talked back a few slides back about lithium-7, lithium-7 has 3 protons and 4 neutrons. That would be, the mass number would be 7 of that isotope. Lithium-6 was the one with 3 protons and 3 neutrons, so that would be the mass number of that isotope. If you assume that lithium was 50% lithium-7 and 50% lithium-6, and you took the average of those numbers, then the atomic mass of lithium would be 6.5, halfway between 6 and 7. It's not, and the reason is because the vast majority of lithium atoms are lithium-7. So the atomic mass for lithium-7 for lithium is going to be much closer to 7 than it is to 6. Very few lithium atoms are lithium-6. Okay, so again, atomic mass is the average mass of all the isotopes of an element. Mass number is the mass of one specific type of isotope of that element. Okay, now you're going to learn how to read the periodic table and use it to draw an atom of a particular element. So the rows in the periodic table are called periods, although oftentimes we'll still just call them rows. And the columns in the periodic table, that's the up and down, those are called groups, although oftentimes we'll still just call them columns. So period and row mean the same thing. Column and group mean the same thing. Now each period represents a new orbital. So the very first row has 2 elements in it, hydrogen and helium. It has 1 orbital. Hydrogen has a proton in its nucleus and an electron in that first orbital. Helium has 2 protons in the nucleus and it has 2 electrons in its first orbital. Now, once you get over to helium, you're at the end of the first row, and therefore that's the end of the first orbital. It cannot hold any more electrons than those 2 electrons. When we go down to the second row, that represents a second orbital. So those elements from lithium on the left over to neon on the right of the second row also have a first orbital with 2 electrons. They filled that first orbital up and now they're going out. The electrons are going to go out to the second orbital. So what happens is lithium has 3 protons in the nucleus and 3 electrons. 2 of them are in the first orbital and 1 of them is in the new second orbital. Beryllium, same thing. It has 4 electrons. It's the 4th element, has 4 protons, 4 electrons. 2 of them are in the first orbital, and 2 of them are in the second orbital. So for a total of 4. Boron has 5 electrons. 2 of them are in the first orbital and 3 of them are in the second orbital. So each new element adds an electron to the second orbital until you get all the way over to neon on the right. It has a total, it's the 10th element on the periodic table. It has a total of 10 electrons. 2 of them are in the first orbital and the other 8 are in the second orbital. And that's all the second orbital can hold is 8 electrons. Once you get to neon, Ne, you've filled up the second orbital. It's full. It can't hold any more electrons. So now we go down to the third row and we add a third orbital. So now for sodium, Na, the first orbital is filled with 2 electrons. The second orbital is already filled with 8 electrons. And now you're adding 1 electron to the third orbital. So that would be sodium. Magnesium next to it, again, full first orbital, full second orbital, and you have 2 electrons in the third orbital. And you do that all the way across until you get to argon, Ar. And that would totally fill up the third orbital with 8 electrons. So now you have 3 full electrons at the end of the third row. Now you go down to the fourth row. And so potassium, which has the letter K, atomic symbol is K, has a full first orbital with 2 electrons, a full second orbital with 8 electrons, a full third orbital with another 8 electrons, and then potassium has 1 electron in its fourth orbital. Calcium has 2 electrons in the fourth orbital. First 3 orbitals are full, 2 electrons in the fourth orbital. Now, the blue, those are the transition metals, the light blue. They do not contribute electrons to this. It's different. They do not contribute valence electrons. We said that back in a previous lesson. Only the first column, the 1A, the 2A, and the last 6 columns, the 3A through 8A columns, those are the only ones that contribute valence electrons. The transition metals, those light blue elements, do not. So once you get to calcium, you skip over the light blue to gallium, which is Ga, and that has 3 electrons in the fourth orbital. Germanium, Ge, has 4 electrons in the fourth orbital, and so on, all the way over to krypton, which fills up the fourth orbital with 8 electrons. And anyway, you get the point. So each new row represents a new orbital. Now the orbitals, as I said earlier, are a little more complex than just circles. We'll study that later on in the course. But for right now, just assuming that they're circles, the transition metals, those light blue ones where it says no valence electrons, just forget about those for now. And we'll deal with that later on. So each group, that's each column, represents an additional valence electron. So valence electrons. So look at the first column. Hydrogen, remember what we just said, that it has 1 electron in its outer orbital, which is its first orbital. Look at lithium. Remember we said that you added a second orbital once you got to the second row, and lithium is the first element. It had 1 electron in its outer orbital, its valence orbital. Sodium, its valence orbital is the third orbital, and it has 1 electron in that outer orbital, that valence orbital. Same with potassium, K. Potassium has 4 orbitals. It has 1 electron in that fourth orbital. Similarly, the second column over, those are the alkaline earth metals. Beryllium has 2 electrons in its. Notice helium, by the way, is over on the right-hand side. And the reason they put helium way over on the right, it has 2 electrons also in its valence orbital. That's the first orbital. But they put it over on the right because it's a noble gas, and it has characteristics of a noble gas. So it's kind of the oddball in that it does have 2 valence electrons, 2 electrons in its outer orbital, but you don't put it in column 2A. You put it over in 8A. But beryllium, it has 2 orbitals, and it has 2 electrons in its second orbital. Magnesium, Mg, has 3 orbitals. It has 2 electrons in its third orbital. Calcium, Ca, has 4 orbitals, and it has 2 electrons in its fourth or valence orbital. So that's how you do this. And then it continues across the column 3A with boron, aluminum, gallium, has 3 electrons in their valence orbitals. Carbon, silicon, germanium has 4 electrons in their valence orbitals. Again, each one has a different number of valence orbitals. A different number of orbitals, I should say. In 5A, nitrogen, phosphorus, and arsenic each have 5 electrons in their valence orbital. For nitrogen, it's the 2nd orbital. For phosphorus, it's the 3rd orbital. And for arsenic, it's the 4th orbital. Group 6A, oxygen has 6 electrons in its 2nd orbital. That's its valence orbital. Sulfur has 6 electrons in its valence orbital. That's the 3rd orbital. And selenium has 6 electrons in its valence orbital. That's the 4th orbital. And then it continues on down 5th and 6th. Okay, then the halogens. Those are called the halogens, second to last column. Fluorine has 7 electrons in its 2nd orbital, its valence orbital. Chlorine has 7 in its 3rd orbital. That's its valence orbital. And bromine has 7 in its 7th orbital. That's its valence orbital. Okay, and then finally the noble gases are full. They have 8 electrons. They have a full valence orbital. So helium, its valence orbital, the 1st orbital, can only hold 2 electrons. So it doesn't have 8 electrons. It has 2. That's the exception. But everything below it, neon has 2 orbitals. The 2nd orbital is its valence orbital, and it has 8 electrons. It's full. Argon below it has 3 orbitals. The 3rd orbital is its valence orbital. It holds 8 electrons, and it's full. Krypton, same thing. It has 4 orbitals. The 4th orbital is its valence orbital, and it holds 8 electrons. The reason they're called noble gases is because all the other elements want to have a full octet, a full valence orbital. We'll learn that principle in a few lessons from now. But for right now, once you get to that 8th row, you filled the valence orbital and you move on to the next orbital on the next row down. Okay, now we're going to build an atom for the rest of this lesson, and you're going to get some practice at doing this. So what you see is I've put a part of the periodic table up there. What I've done is taken the space between boron. If you look at a periodic table, there's a wide gap between beryllium and boron, elements 4 and 5, and between magnesium and aluminum, elements 12 and 13. That's where the transition metals are down below it. So what I did is I just squeezed that together so that it saves space, so that it doesn't take up too much space. But that's the correct order. You see elements 1 through 18 there, the atomic numbers 1 through 18. So we're going to learn how to diagram an atom based on this, and we're going to use silicon as our example. So if you look at the spot where silicon is, you can see that it has an atomic number of 14. Its atomic symbol is Si, its name is silicon, and it has an atomic mass of 28.09. That number is closest to 28, which means the most common isotope of silicon will have a mass number of 28. That means a total of 28 protons and neutrons. But some isotopes of silicon might be 29 or 30, and therefore it brings the average up a little bit from 28 up to 28.09, okay? We don't have to understand exactly how many there are, but just understand most silicon atoms have a mass number, most isotopes of silicon have a mass number of 28. That means 28 protons plus 28 neutrons equals an atomic mass of 28. Okay, the scoreboard is just a way to keep track of what we're learning, what we find out. So protons, electrons, neutrons, how many of those in other words, how many orbitals, and how many electrons in the valence outer orbital. Okay, so let's go ahead and do this. And I recommend you write this out as you do this just to kind of get the practice, and then I'm going to have you do a few on your own on the lesson. So here goes. So silicon has an atomic number of 14. So that means that's the number of protons. That's what defines it as silicon. So it has 14 protons, and if it's electrically neutral, and all atoms are born electrically neutral, it will have 14 electrons. Same number of protons positive as electrons negative. So that's this number right here. So what we can do is we can fill in our scoreboard with 14 and 14. The atomic number tells us in an electrically neutral atom how many protons and therefore how many electrons. All right, now that rectangular box down there with protons and neutrons is the nucleus of the atom that we're going to draw. Draw it as a rectangle rather than a circle, so it doesn't, so you don't get it confused with the orbitals. So that's the nucleus right there. It has protons, it has neutrons, and we now know that it has 14 protons. So we can go ahead and fill in the nucleus with 14 protons. You don't have to draw 14 little circles with plus signs. You could do that. That's kind of tedious. So we'll just write the number 14. But that means there's 14 of those little circles with plus signs there. Okay, let's move on to the next step. Oh, and there's the 14 electrons, but we're going to put them off to the side for right now. So if you count, there's 14 electrons over there on the side. Okay, now we round the atomic mass to the nearest whole number. This is the mass of the most common isotope of silicon. So we just said that, and that's silicon-28. So we're going to work with silicon-28. So we take that number and we're going to round it. So you know, I think most of you know how to round, I hope. You take the number after the decimal, which is 0. If that number were 0, 1, 2, 3, 4, you would round it down to 28. If it were 5, 6, 7, 8, 9, you'd round it up to 29. You're only interested in the decimal, the number right after the decimal, not the 9. Okay, so in this case it's a 0, so it's going to round down to 28. So there we go. We just replaced that 28.09 with a 28 right there. Okay, so that's the mass number of the most common isotope of silicon. So now we can fill in, well, not quite, I take that back. Now we can go ahead and calculate how many neutrons we have. So we can calculate the number of neutrons by subtracting the atomic number from the mass number. So the mass number is the total number of protons and neutrons. We said that. If it has a mass number of 28, and each proton is 1 atomic mass unit, and each neutron is 1 atomic mass unit, then 28 must be the total, the sum total of all the protons and neutrons. So that's 28. So you see that appear in the green box there. Minus the atomic number, and that's the number of protons. We've said that already. So that's going to be 14. And what you come up with then is 28 minus 14 is the number of neutrons. And that's 14. Okay, if I have a bag of 28 apples and oranges, and I ask you how many oranges there are, you'd say, I don't know, there's 28 apples and oranges. Well, if I say 14 of them are apples, there's 28 apples and oranges in the bag, and 14 of them are apples. How many are oranges? You'd say, oh, 28 minus 4, it must be 14. There must be 14 oranges in there. Same thing here, okay? So now we know the number of neutrons. So we're going to fill that into our scoreboard. And we're also going to fill it into our nucleus. So now our nucleus is done. We have 14 protons and 14 neutrons. That adds up to 28. That's the mass number of the most common isotope. Now orbitals. How many orbitals does silicon have? So because silicon is in the third period and row are the same thing, it has 3 orbitals. So everything that you're seeing covered in green there is in the third row and has 3 orbitals. We're just interested in silicon right now, but all of those elements in green there have 3 orbitals. So what we're going to do is go ahead and place those orbitals in our scoreboard. So there's 3 orbitals, and now we're going to go ahead and place them in our diagram. There's the first orbital, there's the second orbital, and there's the third orbital. So now we have our 3 orbitals. Now we place the electrons. The first orbital gets 2 electrons, then it's full. The second orbital gets 8 electrons, then it's full. And the final 4 electrons go to the outer orbital, that's the valence orbital, and they are spread out. So I want you to watch how I place the electrons, and this will come in handy later on. Think about when you walk into a movie theater and it's empty and you sit down and somebody you don't know comes in and they sit down, but they don't sit right next to you because they don't know you. Somebody else comes in, they don't know anybody else, they sit somewhere else. And so everybody's kind of spread out in the theater. Then as the theater starts to get full, the people that are coming in later have to start sitting next to people that they don't know, so that's just the way it works, okay? It's the same thing with electrons. And what you're going to do first is spread them out around each orbital at first, and then you're going to start pairing them up. So for the first orbital, it can only hold 2 electrons. We said that the first row, first orbital, has 2 elements. It can hold 2 electrons. So we're going to take those 2 electrons and place them there. Now they go side by side because that first orbital can only hold 2 electrons. Now it's full. The other key to electrons being paired up is it means they can't pair up with other electrons. We'll talk about that concept later. If an electron is unpaired, it can bond with the electrons from another atom to form a chemical bond. But if they're paired up, they can't do that. Okay, so now we're ready for the second row. It can hold 8 electrons. So watch how I place them. Oh, by the way, the first orbital is now full. No vacancy. You can't put any more electrons there. So now we're going to start with the second orbital. We're going to put the first one there. Now, why do I put it on the bottom? Just because I felt like it. You don't have to do that, but it'd probably be helpful. Just do it the same way that I'm doing it. That way we're always diagramming our atoms the same way. Now, where's the second one going to go? Remember, we said it was going to spread out. So we're going to put it over here on the left side. What about the third one in the second orbital? We're going to put it up here on top. And what about the fourth one in the second orbital? We're going to put it there. So now we have 4 electrons in the second orbital, but the second orbital can hold 8 before it's full. So now we're going to take the fifth one. It can't spread out anymore, so we're going to pair it up down there on the bottom. The sixth one is going to pair up over here. The seventh one is going to pair up here. And the 8th one is going to pair up right there. So now you have a full second orbital. It's holding 8 electrons. Again, you know it can hold 8 electrons because there's 8 elements in the second row of the periodic table. That means 8 electrons is the maximum. And so now there's no vacancy in the second orbital. You can't put any more electrons in the second orbital. So now we're ready to go on to the third orbital, and we're going to fill that up the same way we did the second. The first one we put down at the bottom. The second one we put away from it. The third one we put up here. The fourth one we put there. And now we're out of electrons. So we've completely filled up. We've used all of our electrons. Now you notice the third orbital is not filled. And remember what I just said, that unpaired electrons can match up with electrons from other atoms to form chemical bonds and chemical compounds with other atoms of other elements. So that's the significance of those 4 valence electrons. So there's 4 valence electrons. Those 4 outer shell electrons, outer orbital electrons, are valence electrons. There's 4 of them, and they're all unpaired. So that means that silicon can bond on 4 sides like that, okay? Again, I'm getting a little ahead, but that's the concept of paired and unpaired electrons. So anyway, the number of electrons in the valence outer orbital is 4. We can see that. But how would we know that? If we wanted to know that and not have to draw this entire atom, how would we do that? Well, remember what we said about the groups or the columns? So we know that silicon has 4 valence electrons because it is the 4th element in its row. So if we count, we start with sodium on the left, then magnesium has 2 valence electrons, aluminum has 3 valence electrons, and now we're over to silicon, and that has 4 valence electrons. Now we could see that by looking at our diagram, and then we'll fill in our scoreboard there with the 4. So we filled in the scoreboard, and we've completed the diagram of the atom. So we could see from our diagram that silicon had 4 valence electrons, but what if we wanted to know that? And there's reasons why we might want to know that without having to draw this whole diagram. Then you can simply count how many positions from the left side of the periodic table, not counting transition metals if it's in one of the transition metal rows. How many elements from the left? Silicon is the 4th element from the left, so it has 4 valence electrons. Okay, that takes care of this lesson. There was a lot of terminology, and you learned how to read a periodic table in terms of how to diagram an atom. I'm going to have you practice that on this assignment. So go ahead and get on this assignment. This assignment I would like by Tuesday of next week, regardless of which period you're in. Go ahead and have this in by Tuesday of next week. And that's it for this lesson. So have a nice weekend, and we'll see you on Monday or Tuesday.